Back to calculus 3. Again, we are working on 6.4 Green Theorem. This is the Green Theorem, which says when you work with a line integral for a closed curve, and then it could be calculated as a double integral. The double integral of the difference of cross partial derivatives. The difference, it is in the fashion of dq dx minus dp dy. I think I did 2 examples already, both of these, 6.38, 6.39. I suppose, you see, like in the first case, without using Green Theorem, we need to use calculate the 4 line integrals, right? Because indeed there are 4 line segments. And I'm saying Green Theorem gives us a more efficient way to calculate line integral. And also the second example, you can give a try. If you don't use the Green Theorem, it's impossible. It's impossible. It's impossible. Nearly impossible, I want to say. Really, I think it is impossible to calculate the line integral directly. But realizing this is a line integral on a closed curve. Beside the curve, it is circle. So with the Green Theorem, we really don't need to bother about antiderivative sign or this e to the sine, those things. And we convert a line integral into a double integral by taking the difference of cross partial derivatives. This difference, it is calculated as dq dx minus dp dy. And then we get the result in a rather easy way. Okay, so a line integral is converted a double integral when the curve is closed. And for the next example, and also I want to show you, somewhat interesting enough, it isn't possible. Okay, when you want to calculate a double integral, you can convert the double integral into a line integral. So this is also the example from textbook. It is from 6.40. Okay, we want to calculate the area of the ellipse, the enclosed by the ellipse here. And this is what I did first. In general, in most cases, the double integral we covered, we say it is the volume of solid under a surface over region in the xy plane. And also in the spatial case, when we have double integral of 1, I don't need to put a 1, but anyway, I just want to emphasize there's 1 here. Double integral of 1 over the region, and then the double integral, it is the area. So I say in this case to consider the area enclosed by the ellipse, it is double integral of 1. It is double integral of 1. And then somewhat you can make different arrangements. Okay, the thing is you want to make sure this is double integral because we are considering the Green Theorem. So you may want to generate some vector valued functions such that dq dx minus dp dy is 1. There are different ways. I'm just showing one way. You take a look if it makes sense to you. dq dx, that is 1/2, right? Then dp dy, that is negative 1/2. 1/2 minus negative 1/2, it is 1. It is 1. This vector valued function can be considered differently. The only requirement here is you want to make sure dq dx minus dp dy is 1. There are different ways. Okay, this is just one way. And so I know this double integral 1 represents the area. And according to the Green Theorem, a double integral can be converted back into line integral. So the green double integral, maybe I still put a 1 here. The double integral can be converted into a line integral. That's according to the Green Theorem. And then furthermore, For this line integral, because it is the curve in the circle region enclosed by circle. So the curve we consider here, it is circle. And usually, well, I just write out the double integral, it is p dx q dy. Certainly p is negative y over 2, q it is x over 2. So curve, it is a circle. When we have a circle, we usually consider using the polar coordinates. So I replace x with a times cosine theta, y with b times sine theta. Polar coordinate representation from ellipse. Okay, x with a times cosine theta, and y is b times sine theta. And then you see the line integral can be calculated directly using the definition, right? This time. Okay, it is an integral in terms of theta only. Theta is running from 0 to 2 pi. Still may look pretty long, but look closely. D of cosine theta, certainly you want to take out this a first. D cosine theta, it is negative sign, right? Negative tends to be plus. Negative tends to be plus. Sine theta, that is sine squared. Then for the second part, 1/2 a times b together. Derivative sine, that's cosine. So we have cosine together. So take out 1/2 ab, and then the integrand, it is sine squared plus cosine squared is 1. So we are really having the integral of 1 with respect to theta. That 1/2 times ab still stays. So accordingly, we just figured out, using calculus, the area enclosed by the ellipse. It is pi times AB. So this is another way to consider a line integral, using Green theorem, or really should I say precisely, in general, most of the time we consider Green theorem converts a line integral into double integral. And also some cases like the one we just finished, we really want to convert a double integral into a line integral. Okay. And then we will take a break, and I'll double check if we need to talk a little more. And thank you for watching.